So, hello everyone. Welcome to today's nuclear engineering summer school lecture. So for today, we have a guest speaker. I'd like you all to welcome Pierre Marleau. He's a distinguished staff physicist at Sandia National Labs. He has received his PhD in physics from the University of California at Davis in 2007, with an emphasis on experimental high energy particle physics. Pete has over 19 years of experience in radiation and nuclear detection, system design, optimization, fabrication, and deployment. He has developed several fast neutron detection, imaging, spectroscopic systems for applications ranging from treaty verification to nuclear engineering, response to homeland security, and a nuclear nonproliferation. Happy to have him here today with us, and he has also indicated that you are all welcome to ask and post questions in the chat. And as the talk goes on, I can jump in and ask them for you. So I'll hand it over to Pete.
Thanks, Ricardo. Again, I said you didn't have to read all of that. Good morning, everyone, or afternoon, as the case may be. Let me share my screen. Okay, yeah, so I'm Peter Marleau from Sandia National Labs out in California. I've been there about 16 years. A lot of my work has been in the development of various neutron imaging systems. Today, I wanted to dust off some material that's now it's about 4 years old, but it's been this work was really exciting and it's sort of been parked on hold for a while. But I enjoy talking about it and I felt compelled to, which was some of the correlated timing work that's related to imaging. In fact, hopefully I have time to get to 3D imaging. But you can see that the title of my talk is not what was on the agenda. I originally I was planning on giving a talk about when imaging, what applications imaging is useful for and when not to use imaging, which is a lesson I've learned over the years. So I kind of liked it when the title of my talk was TBD, so I could do whatever I want. But this talk will be in a few parts, and I'll start with imaging in general and some of the work that I've done over the years. And some of that will be lessons learned about when imaging is useful and how it's useful. And then I'll shift gears a bit and talk more about material characterization and imaging using a technique that I developed with a Michigan student back then. He was a Michigan grad student, Mataush in Montreal. A lot of the material that is in here came from him, and if you're interested, give his thesis a read. There's a lot of good material there. All right, let me get going. Oh, and like Ricardo said, please don't be afraid to ask questions. Just speak up. I'm happy to do it as we go, and I'll field them. All right. So motivation. My work here at Sandia, my department, the Radiation Nuclear Detection Systems department, is a bit unusual in that a lot of the national labs, you'll find the departments own a mission. So there will be a department devoted to arms control or safeguards or nuclear emergency response, and they learn the needs and requirements of sponsoring organizations that are devoted to those missions. Our department's a little bit different, and I appreciate it that we're generically an in-house radiation detection development capability, independent of a mission. So it's been fun over the years that I get to learn those needs and requirements from various missions like arms control and non-proliferation in general, and figure out how optimize and design radiation detection systems to meet their needs. And what's nice about that is there's a lot of overlap in requirements between the various application spaces. This Venn diagram is not meant to be accurate in any way. It's just to illustrate that there is a lot of commonalities, but there's different design drivers to optimize toward. But in general, the commonality between all of these is special nuclear material, and whether that's to detect it or localize it or characterize it. And I'll talk more about those divisions of tasking. And this is sort of saying more of the same, but with a imaging slant. Our department has become known for, in particular, neutron imaging. So I try not to make that my hammer and then find every mission space a nail, but that tends to happen. And so we've done a lot of thinking about how imaging and then requirements of these missions changes the design and the requirements of an imaging system. And generally, the applications fall into 2 or 3 categories. There's, on the left, there's missions that require just detection of S&M, and maybe localization, but by that I mean you don't need high resolution imaging, it would be good to know that it's over there, or in that container or that container stack. But really the game is using imaging to detect small signals in the presence of a background. And that background could be time varying or varying in terms of angular position. So it's important to understand the background and use imaging really to reduce the uncertainties in the background in a low signal environment. On the right, these are areas where you know where the thing is, or that there should be S&M somewhere, and that it should be in a certain configuration. For example, in arms control, treaty verification, or warhead confirmation in particular, there will be a declaration. And this is mostly true for safeguards also. There's a declaration that nuclear material is present, and that it is a certain form, and then it's maybe a certain geometry. And your job is to verify that. And in these applications, higher resolution and more characterization of the nuclear material, not just that it's present, is required. And I forgot to mention, nuclear emergency response would be a case where there's suspected nuclear material in an unknown state, in a unknown, it's a black box, and you want to learn as much about it as you can. And again, higher resolution and material characterization combined is necessary there. Yeah, so this is sort of stating this again, that there's really 3 very different needs here. That detection is not about reconstructing an image. It's really about, is it present? And you really have to think about, what is imaging doing for you in this case, if you want to use the imaging hammer to apply it to detection. Whereas localization requires some sort of directionality, and it's mostly also is sort of an extension of detection, but you also are interested in where something is. Whereas in imaging, you're probably doing full image reconstruction, And I won't get into that today, but there's a lot of things we could borrow from medical imaging in terms of image reconstruction and the design of detectors that we're also involved in. And then you might be asking questions of the reconstructed image after the fact. For example, dimensions or locations of how different materials fit together. So I just wanted to give a plug. So I'm going to run through this really quick. We've designed a lot of various different kinds of imaging systems over my career over the last 16 years. I've been a part of most of these. I'd be happy to talk about them maybe offline. If anybody has questions, feel free to email me. So there's a few classes of imaging systems that we've been developing. One is aperture imagers. This includes coded aperture imaging. This is on the left. There is a neutron coded aperture imager that we collaborated with Oak Ridge to develop. Time encoded imaging is similar to coded aperture, but you have a single pixel and you rotate a coded mask around it. The one on the right here is designed more for detection. I'm going to talk a bit more about that after in a few slides. There's neutron scatter camera development. I think you've seen some of this in previous presentations. When I first started at Sandia, I was brought on to develop the neutron scatter camera, which is that one on the left there. It's about a cubic meter of detector. This one had 32 large 5-inch diameter liquid scintillators positioned in 2 planes. But a lot of the work over the last decade or so was taking that very large detector system that's really kind of a laboratory prototype, and its electronics there you can see was in a full rack of VME electronics, and making it more mobile and useful for field use. The middle one is the mobile imager for neutrons for emergency response, or MINER. It's 16 3-inch liquid scintillator cells, but it's in a much more compact form factor, and everything it needs is right there. It's a 16-channel digitizer and a small computer. Well, actually, it's showing a laptop, but there's an onboard computer. It's completely autonomous. And then more recently, there's a single volume scatter camera work, which is instead of using separate cells for a scatter camera, trying to reconstruct multiple interactions in a single volume of scintillator. All of these have been stepping toward increasing the efficiency per unit volume of material, so we can make it more compact. Because I didn't mention it, but it's going to become a theme. The trade-off, there's always a trade-off between the efficiency of detection and imaging. And in general, the better the imaging resolution of your imaging system, the lower the efficiency is going to be. And a lot of the R&D has been in trying to overcome that in one way or another. So this is a little bit more on MINER. It's gone through several demonstrations. For example, that bottom left, it was used in demonstration to detect and localize radioactive sources in nearby buildings from a high rise. That middle one is a version of MINER called Stinger that was actually based, it's still being based, and it was designed to fit in the back of a vehicle and be driven around. And then it's been through various demonstrations for search and localization of materials. There's more on the single volume scatter camera. There was a lot of work there. There were 2 versions of it. One was a segmented version that looks a bit like what's being developed there in Michigan, but also a single monolithic volume that's not segmented was developed. And then, yeah, this is another one of my babies, which is a time-encoded imager that's designed specifically for warhead verification. Again, I won't get into that, but that's fun, and I'd be happy to talk about it with anyone that's interested. And then I won't say much about this, but we're dabbling in alternative signatures that aren't even radiation detection based, because really it's whatever you can do to solve the problems of the mission. In this case, using electromagnetic signatures for either the detection and characterization of nuclear material, or just the detection of shielding material that might be used to reduce or eliminate the radiation signatures. Okay, and like I said, in general, and again, this isn't meant to be quantitative in any way, we think of these systems as sort of existing on a space of imaging resolution on one axis and effective area or efficiency times area on another. And standoff, detection problems live way on the bottom right side, where you don't really need resolution, but you definitely need effective area. Whereas a lot of those like arms control and safeguards and nuclear emergency response live up in the top left, where, well, at the top anyway, where imaging resolution is important. Effective area is really mostly important because you want to do things in a timely manner. If you had an application where you had days to measure, that would be awesome. But usually people are tapping their foot and being impatient within 30 minutes. So there is really a drive to push things at to the top right in those applications. All right, and so I wanted to take just a few minutes to show some work that was done maybe 5 years ago that really kind of illustrates the detection versus imaging issue. And I hope I'm not sounding redundant here, but really if the problem is about detection, and I'm picking on standoff detection here, but this really applies to any time where there's a low signal in the presence of either a high background, or it doesn't have to be high, but it could be varying and or unknown. But in general, let's take, for example, weapons grade plutonium, and a significant quantity as determined by the IAEA is 8 kilograms. That just neglecting multiplication, that gives you about 5 times 10 to the 4th neutrons per second per kilogram. So if your problem was to detect that material, even just bare, not shielded, but 100 meters away, we're talking about a little over 1 neutron per second per square meter. And the background at sea level is something like 5 times 10 to the minus 3 neutrons per second per square centimeter. So that equates to about 50 neutrons per second per square meter. So even this is just, we're not even talking about detecting anything yet. This is what you're faced with, about 1 neutrons per second per square meter in the presence of 50. And these are all fission energy neutrons we're talking about. So let's pretend somehow you made a 100% detector that's 1 square meter in area. To reach 5 sigma detection, you need a minimum of 13 minutes. And that's right. But often, well, not often, you are not going to reach 100% efficient. And in fact, 10% efficient is you might be happy with. But now we're talking about 2 hours. And again, this is, people are going to be impatient in 2 hours. And there's not many applications where you can sit there for 2 hours to clear that area. And what's worse is often what you're fighting is not just the Poisson statistics of those 50 counts per second per square meter, but you might not know that it's 50. You might have some uncertainty in that background value, which means if, in the case of a 10% efficient detector, you're never going to detect it because any uncertainty in any potential excess from the source is hidden in that uncertainty. And we've used this in the past as an argument for why imaging or directional information helps, because the neutron background is relatively well known. You can predict it without a measurement to within maybe 20%, just based on location and elevation and the presence of other materials and where you are. But if you didn't measure it before and you just rolled in, then 20% uncertainty is pretty high, and it's really going to hide the things you might want to detect. So directional information helps by reducing that background, background counting statistics that you're fighting to what's within the angular resolution of a source. And this is a naive sort of cartoon way of looking at it, because imaging systems don't normally work like this. It's not really, you're fighting only what's behind that bin, but you get the idea. You're reducing the background you're fighting to a direction. And also, you can use those other bins, those other angular bins in your image to estimate the background, or at least estimate the uncertainty in the background in a direction. But what if the background were independently known? For example, there are applications like portal monitors or monitoring systems where the detector is sitting there and able to record. Its job is mostly recording background. So in those cases, you have a pretty good idea of what your background is. Then you don't need imaging to determine the background. And especially if the source that you're maybe wanting to detect is moving, or the detector is moving. Again, portal monitor, if it's sitting there recording background most of the day and then a source is driving by, the source term is modulated itself in an expected way, right? It's going to be a sort of a spike as it drives by. Imaging becomes less and less necessary. So it's only useful in those sorts of situations when the source term is low enough compared to the background that you need to reduce the background in the direction that the source is. And then that bit on the bottom is really, one more time, I'm gonna repeat myself. You almost always, well, I haven't found a case where imaging so as to reduce the background does not reduce your efficiency. So if you're applying imaging to a problem, you better reduce the background more than the hit you get in the effective area of your system. All right. So this is one case where we designed and built a directional detector specifically for that problem. It's a time encoded imager. This was 4 very large, well, large vats, 27 liters a piece of liquid scintillator. They were 12-inch diameter, 15-inch deep each, and each one was read out by 4 or 5-inch PMTs that were summed together. We really needed all of that volume just to gain the efficiency in a standoff detection problem like I discussed before. And then these were on a turntable and they would rotate. So they would self-modulate each other, right? They would block the radiation from a direction. So there's no passive material here. They're all actively modulating each other. And what you would get is something like on the right here. These are the modulation patterns as a function of rotation angle. So this is one full rotation. This is the expected pattern of counts you would expect in these detectors as it rotated. So you'd be looking for that kind of modulation in the presence of some offset background to determine whether you detected a source. And just for you detector people out there, one of the biggest challenges in this project was pole shape discrimination. You could imagine having such a large liquid scintillator cell with not great photodetector coverage, trying to get pole shape discrimination out of that. And it was, you could see it was right there on the left. That's not great pole shape discrimination. So in this case, we suffered an efficiency cut because our pole shape discrimination was poor. And here's some results. This was with a 1 millicurie californium source that we took out in a field and measured at different standoff distances. We lost one of the detectors, so this is only with 3 of those cells. So we could detect it out at 100 meters, and we determined that it would take about 720 seconds to do that. Up closer, much quicker, of course. This sort of detection system we actually pitched for clearing a smaller area like a high bay. You might be able to park it in the middle of a large area or a building, not 100 meters out, but tens of meters, and in minutes you should have or tens of minutes you could determine that there's no material above, or no unshielded material above some mass present. Okay, how am I doing on time, Ricardo?
So far, so good. You still have 30 minutes.
I'm at 30 minutes, okay. All right. Well, are there any questions about any of that? Because I'm going to change direction a bit now. Okay. Yeah, so I was looking for material to present for today, and I was reminded of some of the time correlated imaging work that I did with Matt from Michigan, and I was reminded of how interesting and fun it was. So I want to present this, and if anyone's looking for a research topic out there, I would love to get back into this, and I'd be happy to talk with anyone about any of this work. This is one of those application spaces where it's really about characterization, a characterization of nuclear material. So you want to know, well, one, is it nuclear material or some other neutron emitting material or gamma emitting material? But also, is it in a form factor that might be a weapon? And what properties does that have? And so what we're going to do is look at the time correlations between gammas and neutrons as a method of non-destructive assay of the nuclear material and its geometry. All right, so I stripped out a lot of this because I hope everyone knows by this time what nuclear material is. And the special nuclear material in particular is what's of interest is the U-233, U-235, and Pu-239. There's lots of nuclear materials, but the special ones are those 3. And what makes it so special? I mean, the bottom line is it could be made into either a reactor or a nuclear weapon. It could sustain fission chains. And really, they're physical properties that make them so special, right? That this on the right is the cross section for inducing fission in these various materials versus neutron energy. And you could see those three, U-233, Pu-239, and U-235, have a high cross section at low energies. And they'll emit multiple neutrons when they fizz. So those are the requirements for sustaining fission chains and potentially going critical or supercritical. Other things can be induced to fission, but at higher energy neutrons, and so they're not likely to be induced to fission by the energies of neutrons that come out from a fission. All right, and so that property that sustaining a fission chain is unique to special nuclear material, and that's one reason people use correlated neutrons as a method to characterize that nuclear material because it's unique. All right, I'll go pretty quickly through this, but basically the quantity, the metrics to define or characterize nuclear material in this way come down to basically a quantity that is related to the fission chains that occur within the material. And it's, you'll often hear multiplication used, which is really the average total neutrons that are created for one neutron that's sort of injected into the material, whether that's by a fission or some external source. And the K is it's really the number of neutrons in one generation divided by the number of neutrons in a preceding generation. So this is an important characteristic of the nuclear material and tells you how basically how long are the fission chains. All right, so a lot of what's been done over the century, we're not there yet, many decades of knowing there's nuclear material and trying to characterize it. There's various methods, radiography, gamma spec, just total raw neutron counts, and then I think you learned some of this in previous presentations, multiplicity analysis, basically counting the number of singles, doubles, triples, multiplets as a function of coincidence time window, and looking for excess variance above just raw counts. These have been developed for decades, and all of them have some limitations and drawbacks. I won't, most are very well developed, and there's a lot you can learn. But for example, gamma spec, there's a lot you can learn from a gamma spectrum. But the limitations are, the low energy gammas that are characteristic of some materials are easily shielded or attenuated by the material itself. So it's difficult to assay a total mass, for example, in some situations where there's a thick, the nuclear material is thick. So I won't get into all of the drawbacks and limitations, but except to say the focus of this work was to target neutrons and correlated neutrons, and in particular doing something beyond what is normally done, which is a neutron capture based method of detection, historically based on helium-3 detectors. And one reason to seek to go beyond that is that the detectors themselves have a relatively slow response. And there's a lot of information to be learned in very fast timeframes. The fission chains that develop within the nuclear material occur on the order of nanoseconds. And if neutrons leak out of that nuclear material and are reflected back quickly, there's more information to be learned on the order of tens of nanoseconds. And all of that gets sort of wiped out in these types of detectors because the response to the detector is much slower than that. And further, we're seeking to develop a method where the efficiency is not so important. And I'll touch more on that. I'm sure you've seen this before. All right. Yeah, so prior methods are basically, the game is to detect deviations from what you'd expect if you had completely uncorrelated random counts in your detector. So for example, if it were completely uncorrelated and you got 100 counts in your detector, then you'd expect the variance in counts around that to be the square root of 100 or 10. But if you have correlated emission, and so some of those detection events are correlated, you'd expect something that deviates from that Poisson expectation. And so that's done in multiplicity counters by basically seeing how often are you seeing more higher correlations, higher multiplicities than you'd expect from random chance. And then there's a whole set of complicated equations that I'm not going to get into that relate your the number of times you see a single neutron by itself in a time window, two in a time window, and 3 in a time window, and you could keep going to various properties. Some of the properties are of the nuclear material itself, which is why we're doing it, like the spontaneous fission rate and the multiplication of the material, and how many, this is basically how much of the neutrons that are generated come from an uncorrelated source versus a correlated source. And then these are just physical properties of the material related to how many neutrons are emitted on average from the spontaneous fission and induced fission. But you'll note there's also efficiency terms in here, so you have to know your detection efficiency, and the higher you go in multiplicity, the higher that the power that gets raised to. So by the time you're at triples, you're cubing your efficiency in these equations, and often people don't go much beyond triples because the uncertainties are already too high to do something with. So there are a lot of unknowns and only a handful of things measured. And so that there's really an art to this type of analysis. There's a lot of knobs to tweak to match a model to data, for example. All right, so what we're doing is targeting multiplicity 2 correlations only. And I won't go into the details of why, but we decided gamma neutron, so that it's not really multiplicity 2, it's a gamma and a neutron, is what we're after. And we're looking at those because we want to, rather than looking at how often you see different multiplicities, we want to target the timing between events. And so a gamma is a nice clean clock start for us because it always takes the same time to get from where it was born to your detector. And then the neutron carries information about the development of fission chains within the material. All right. And we're also, seeking to use scintillator detectors that mostly because, well, one, they're fast, on the order of nanoseconds timing resolution or better, but also they have some measure of the neutron energy, and they're many organic scintillators are pulse-shape discrimination capable, which means in the same detector, you're able to detect both the gamma ray and the neutron. So we don't need separate detectors for gamma rays and separate ones for neutrons. You do it all in the same detector. So again, we're looking for a gamma ray and a neutron correlated in very short time spans. And we're going to do something with the time between the gamma and neutron to characterize the material. All right, and basically, what we're going to do is that, so if a gamma and a neutron were born from the same fission event, and you're detecting it some distance away, then, and this delta T and gamma is the time between the neutron and gamma that you detect at your detector system. If you knew the energy of the neutron, you could calculate what this delta T should be. Basically, R here is the distance traveled. So the time it takes a gamma ray to get to your detector is fixed. It's the distance over the speed of light. And you could calculate the time it takes for a neutron to get to your detector. It's 1/2 mv squared is the energy, so you just invert that. Everything would be known. You would measure the time between a neutron and gamma, and you could calculate it, so it should equal 0. Okay, there's a lot of animations on here. Right, so that term on the left is something you measure. The problem is it's hard to measure the energy of a neutron, especially in an organic scintillator. And I think you might have had presentations on this before. Not all of the energy is deposited in the organic scintillator. So all you're left with is a recoil energy on the proton, which is some value that's less than the true energy of the neutron. So because of that, if you said, okay, let's just use that energy that's deposited in my detector as a stand-in for the true neutron energy, you will be overestimating the time that it takes to get there to your detector, and thus, this term will be larger than it should be, and so you'll get something less than 0. Does that make sense to everyone? Hopefully it does. So these now are all measured quantities. If you had a detector is some distance from your nuclear material, you measure the time between the neutron and the gamma, and you have the recoil energy, energy deposited in your detector. You can calculate this value for every correlated gamma neutron that you see in your detector. And notice, efficiency hasn't come into this yet. We're just looking at the timing. And from here on, I'm going to call this term delta TP because it's the time that you would calculate from the proton recoil energy in the detector. This term on the left, we call toffee. Okay, it's a cute term. Here's for you students out there, developing a good acronym is like 50% of the work. So we could argue about whether toffee is a good acronym, but it is one. Time of flight fixed by estimated energy is toffee. So what can we do with toffee? So here's actually a measured, this is what this distribution looks like. This is for a Californium source. There's no multiplication. So every gamma neutron that you see that's correlated came from the same fission and is basically a point source. So what you see is this is uncorrelated noise that you'll just get. And then there's a sharp drop off here at 0 because everything should be, this should always be less than 0 because we're underestimating the energy of the neutron. And then there's some energy resolution effects that make broaden this a bit. I'm going to skip. Okay, I'm going to skip through this a bit because we're low on time. Okay, so if you have a fission chain. Gamma and neutron could be not from the same fission. What you get is, again, we're going to measure this stuff on the left, and you may have a time between the when the gamma and the neutron were born. That time, delta Tg, is actually the time difference between the fission events in the chain that are happening in the nuclear material. And that could happen many ways. If you imagine a fission chain could have many fissions going on, and you're sort of randomly selecting a gamma from one fission and a neutron from another. And so the order of when you know, which one was first, the gamma or neutron in the fission chain, this delta T sub G can be positive or negative. But you are sampling the timing distribution from the development of that fission chain. Okay, yeah, that thing on the left is toffee, and as we defined it, it's always less than the time between fission events in the chain. All right, I skipped this before, so I'm going to skip it again. Basically, so we went on several measurement campaigns and measured, in this case, the Burt ball. If you're not familiar with that, it's 4.5 kilograms of weapons grade plutonium at the device assembly facility in Nevada. And you could put shells of various materials around it, which both changes the multiplication of the assembly, but also you could change the type of reflection that's happening. You could put high Z materials, or a mixture of, or a range of different material types around it that affect how the neutrons are reflected back into the nuclear material. The effect on the toffee distribution, again, that bottom left is what I showed before for a non-fissile, non-multiplying source. Basically, the distribution gets spread by that delta T sub G. There's some underlying same fission distribution here, but because you can sample a gamma and a neutron from different fissions in the chain, it gets spread out by the average timing of the chain. So in this case, in this configuration, this is a bare Burt ball. The multiplication is 4.4, which means on average for every neutron that's generated, you get four neutrons out. So basically sorry, this is not 0, it's 1. Basically the average length of chains is 4-ish. So you're randomly sampling from those 4 fissions, and you get this broadened distribution. And then here we've reflected it, put 1 inch of iron around the Burt ball, you get a higher multiplication. And so you get more spread. The fission chain is longer in time, and there's more fissions. There's more of a chance to grab a gamma and a neutron from different fissions. And so what we tried to do, and this is a thesis work of Mateusz, is use the measured toffee distribution to try to back out what was the multiplication of the nuclear material, and maybe what is the reflecting material, or the reflecting environment around the nuclear material. All right, like, is it bare or is the reflection? All right, so we spent a lot of time with trying to develop physical models and doing some inverse solving, and applying point kinetics theory to what's happening. And in fact, you can do this by doing a two region point kinetics and saying, okay, there's a nuclear material in a core, but there's also a reflector neutron. There's some neutron population leaving the nuclear material, So this is leaving the nuclear material, but there's also some reflecting back from the reflector. And then this is the generation multiplication term. But you could also, there's a coupled equation for the neutrons in the reflector. And so there's stuff coming into the reflector from the nuclear material, and then there's stuff leaking out either by just leaving the system or reflecting back into the core. So you could solve for that, two-region coupled point kinetics equation, and you get this mess. The solution is a double exponential, which is nice, but the terms of the exponential are a complicated relationship between basically the multiplication and some time scales. We didn't label this very well. Neutron lifetimes within the reflector region and the nuclear material. And then there's coupling terms, like this F is the fraction that leave the fissile material, enter the reflector, and then come back. So there's how well coupled are these two systems. And basically you could take that equation and fit it to the Toffee distribution. So how spread out is the Toffee distribution. And you could, in this case, sorry, I'm jumping around so much. Because this is such a sharp edge at 0, you could basically just fit the leading edge of the Toffee distribution. Though even better is to see, convolve, double exponential to this distribution, and until it matches the measured fissile Toffee distribution. All right. Okay, this was the results from actual data that we could estimate the multiplication estimated from the analysis of the Toffee distribution compared to what an MCMT model predicted, and we got reasonable agreement. Okay, any questions so far? That was a bit of a rush. I will say, that it's similar-ish to a Rossi alpha analysis of neutron multiplicity data, except this is all stuff at tens of nanoseconds, and between a gamma and a neutron, not between a neutron and a neutron. Ricardo, how am I on time?
You got about like 6 minutes. 6
minutes, okay. Let me just get to the 3D imaging part because it's pretty fun. We then asked, that proton recoil energy in an organic scintillator is not a good measure of the incident neutron energy. So what if you can get a better estimate? And so, this is one of the imaging systems that I mentioned before, MINOR, which is a neutron scatter camera. So if the neutron interacted more than one time in the system, I'll skip. This was probably shown in previous talks. Normally, normally what we do with this is try to image the incident neutron. But so you could do that. But one of the advantages here is that you also get the incident neutron energy from the sum of the proton recoil energy in the first interaction and the estimated time of the outgoing neutron by the time between these two interactions. So it's a better estimate of the incident neutron energy than E sub p by itself, which is what we were doing before. So we could put this energy in instead of E sub p. and have an even better measure of the true time between fissions within a fission chain. And here, I think we didn't get beyond modeling, and this is sort of, Matt graduated. But this is some, dangling R&D that would be fun to pick up again. If you used that as a measure of energy, you would get some peaky thing instead of some, instead of this this trailing distribution, you'd have a peak to work with a resolution characteristic of the image, minor, and then the effect of different multiplications would be a broadening of that peak, which would be much easier to work with. But I'm going to end here. We realized, so we're using an imager, so we have this cone that you would get from a neutron scatter camera, which I think Ricardo talked about yesterday. He was looking at these cone projections. So you still have that because your neutron scattered twice, but you also have this correlated gamma ray. And so that correlated gamma ray constrains where on that cone they could have originated. So you have this cone, distance to the source from the time between neutron and gamma. There's some complicated math to solve for, but you could solve for this distance to along the cone. And so instead of a cone projection, you end up with these rings. So this is one correlated neutron gamma detection in minor. The solutions where they could have originated fall on this ring. And so just like Ricardo showed yesterday, if you have many of these rings, you could overlap them in the space in front of your detector. And what you end up with is actually a 3D reconstruction. So it's hard to display 3D on a flat screen, but these are two 2D projections of a reconstructed volume. This is actual data. This is in the lab. We took minor and we had 2 californium sources out in the lab, and we were able to reconstruct. This is distance in this view. Their distance and position around the system. And this is our attempt to make a 3D blob. In fact, we spent some time, well, again, like with the HoloLens, I think you saw some of that yesterday, displaying these 3D reconstructions in an augmented reality. Okay, I'm going to leave it there just in case there's questions, but I think there's this area of research, there's a lot more we can do, including if you had a 3D image and you have an estimate of multiplication, this is a question. Can you deconvolve how multiplying those blobs are, which would be really interesting if you had multiple fissile assemblies in the same field of view and you were able to characterize them separately, is not something that can be done nowadays. And then even better is this could work in an active scenario with uranium, which it's possible. I'll just leave it there. All right, I think I'm out of time, and I'd like to make sure I leave time for questions. So
yeah, thanks, Pete. Yeah, thanks for the talk. Yeah, the last bits that you were discussing, yeah, personally, I find really interesting. Yeah, we can definitely talk about that in the future, but we do have one question so far in the chat. They're asking whether or not it is possible to image a single neutron or even capture just a single neutron. Their thinking behind this is that the wave nature of neutrons tells me more about collective motion because that's how we get particles like photons to make a ray. But is it really possible to capture a single particle?
Capture a single neutron, or?
Yeah, that appears to be the question. Yeah, whether or not you can just work on a single neutron basis rather than having to, I suppose, just.
Okay, I'm seeing, yeah, the wave nature of neutrons. Yeah, so all of this was, everything I was talking about is neutrons in the, MeV region. So their wavelength is very, very small, and their wave nature is just about lost. You have to go down to, thermal or lower energy neutrons before you start seeing coherent wave behavior. But it's interesting to think about, because a lot of what happens in the assembly itself, especially in moderating material, is down at that energy. So there could be wave coherent effects happening in the moderating material. But as far as detection, I'm not aware of any, well, aside from, dedicated neutron facilities where they're using, slow neutrons for that purpose. I'm not aware of anyone using the wave properties for detection.
Cool, thank you. We got one more question. Are scattered neutrons in the forward and backward directions, do they have the same probability?
No. And in fact, I skimmed over a lot of stuff, and I apologize, but if you're talking about the organic scintillators, we're only detecting scatters on hydrogen. They'll also scatter on carbon, but the carbon doesn't deposit. Its energy is quenched, so you mostly don't see the carbon scatters. In hydrogen, in fact, there is no single elastic backscatter, because the neutron and the hydrogen nucleus are nearly the same mass. It's sort of billiard balls. You don't get a backscatter. But in general, it's also not true. There's an angular distribution to the elastic cross section.
All right, well, okay. So I guess one more. Can we really capture can we really capture single neutrons for slow neutrons, as you said? That okay, I guess the first person from the first question is just asking if we could really capture single neutrons even when they're slowed, despite the wave nature.
Yeah, I mean, there's complicated nuclear physics stuff going on, but essentially the neutron is absorbed, and then there's breakup of the compound nucleus. Yeah, I'll leave it there. I'm sure nuclear physicists would have a much better answer for what calculations of what's happening in the nucleus, and I'm sure there's wave equations involved. But
right, yeah, no problem then. So I think that'll do it for time. I'd like to thank everyone for tuning in, and also thank you to Pete again for giving this talk. And yeah, I'll stop the recording now.
All right. Thanks, everyone.